Red-green color blindness. Understanding signs, symptoms, diagnosis, prognosis, and treatment and care. So, overview and facts. Color blindness, specifically red-green color blindness, is primarily inherited in an X-linked recessive pattern. The genes responsible for this condition are located on the X chromosome. Since males have one X and one Y chromosome, a single altered gene on the X chromosome will result in color blindness. Females having two X chromosomes, though, would require the mutation on both the X chromosomes to exhibit the condition, making it way less common in females. The mutations often only affect the OPN1LW and OPN1MW genes, which encode the opsins found in the cone cells of the retina. That's responsible for detecting red and green light. Mortality and morbidity rates. Mortality. Color blindness does not affect mortality rates as it is not a life-threatening condition. Morbidity. While color blindness affects quality of life, particularly in activities requiring color discrimination, it does not lead to physical morbidity. It is estimated that about 1 in 12, 8% of males, and 1 in 200, 0.5% of females of Northern European descent are often affected by some form of color blindness. The prevalence can vary across different populations. So the genetic mutations causing color blindness have likely been present for thousands of years in every part of humanity. However, theories suggest that these mutations might have persisted due to some selective advantages in certain environments, although this is still a topic of discussion and research. Color blindness occurs worldwide and affects individuals of all ethnic background. However, the prevalence can differ based on genetic diversity and population-specific genetic traits. It's mostly reported in populations of Northern European descent. Signs and symptoms. Individuals might incorrectly name colors or fail to recognize the correct color of objects. There may be issues with color-coded information like charts, maps, and graphs, and difficulty with everyday tasks like finding ripe fruit, matching clothes, or reading signs and signals. Different specific types of color blindness, and there's different specific types of red-green color blindness. So there's pronopia, excuse my pronunciation, which is absence of red photoreceptors. There's protoanomaly, which is reduced sensitivity to red, deuteranopia, absence of green photoreceptors, and deuteranomaly, which is reduced sensitivity to green. Diagnosing red-green color blindness typically involves a series of tests designed to assess color vision. These tests are usually conducted by an optometrist or an ophthalmologist. So one type of test is the Ishihara test, which is the most common test. It consists of a series of plates and dots, various colors forming numbers or patterns, seen in the top right corner over here on this slide. So individuals with normal vision can distinguish these numbers, where people who don't have normal color vision cannot. This just primarily detects red-green color blindness. There's other types of tests that, for timing purposes, I won't get into, but the most common one is the Ishihara test. There's the Farnsworth, Munsell, 100-hue test, the Cambridge color test, and there's also the anomaliscope test. But moving on, diagnosis and prognosis. The prognosis refers to the expected long-term outcome and potential impact of a medical condition on an individual's life. For red-green color blindness, the prognosis involves understanding the lifelong implications, potential challenges, and ways to manage the condition. Though it's a lifelong condition with no cure, the prognosis for individuals with the condition is generally positive. It does not affect life expectancy or cause additional health problems. It does not worsen over time, and the severity and the type of color vision deficiency remains constant throughout someone's life. With appropriate accommodations and awareness, most individuals can perform very well in settings. Certain careers requiring precise color vision may be challenging or restricted, but many professions are left unaffected. There's various tools and technologies that are available to assist individuals. These include color identifying apps, special lenses, adaptive devices that can help distinguish colors. Some professional and educational settings offer accommodations like non-color coded materials, but there's also safety considerations that people with color blindness should be aware of. They need awareness and adaptive strategies that can mitigate safety concerns, such as interpreting traffic lights and color-coded warnings. Using patterns, shapes, and positions instead of colors can improve safety and navigation in environments. Currently, there's no cure for red-green color blindness, as it is a genetic condition. However, several treatments and care strategies can help individuals manage the condition and improve quality of their lives. Like I said earlier, there's special lenses and glasses, color-corrective glasses. They're designed to enhance color perception. They filter specific wavelengths of light. brands like Enchroma and Palestone offer these products. There's apps and digital tools like Seeing AI, Colorblind Pal, color binoculars. These are all really helpful. Since red-green color blindness is a genetic condition, there's currently no way to prevent it from happening. However, ongoing research into gene therapy may eventually provide options for the future. There's experimental treatments replacing defective genes responsible for color blindness and modifying them. There are some famous people who have red-green color blindness: Howie Mandel, Mark Zuckerberg, Prince William, Bill Clinton, and Aaron Goldberg. I really hope you enjoyed my presentation at PSA and color blindness. Hopefully you've learned a lot and now you feel more educated.